And welcome back as we go ahead and do our next lesson for astronomy topics. We're going to talk about the birth of modern astronomy. Up to this, of course, we've talked about some of the ancient stuff that has gone on, such as some of the things that Greek philosophers and mathematicians worked through, as well as take a look at how astrology kind of first played its role in trying to determine the cosmos and its role in our lives. But now let's take a more modern scientific glance. So one of the things you have to understand is the rediscovery of astronomy and the love for what we wanted to learn about the cosmos. So astronomy really made no major advances in strife-torn medieval Europe. The birth and expansion of Islam after the 7th century led to a flowering of Arabic and Jewish cultures that preserved, translated, and added to many of the astronomical ideas of the Greeks. Now, many of the names of, for example, the brightest stars are taken from Arabic, such are also many of our terminologies that we use, such as zenith. Now, as the European culture began to emerge from its long dark age, trading with the Arabic countries led to a rediscovery of ancient texts, such as the Almagest, and led to a reawakening of interest in those astronomical questions. This time of rebirth, which was known as the Renaissance in astronomy, was embodied first with the work of Copernicus. Now, Copernicus kind of led one of the most important events in the Renaissance, which was the displacement of Earth from the center of the universe. Remember, we had talked about how we had a geocentric model, geo meaning Earth. So Copernicus, who was a Polish cleric in the 16th century, he kind of came along and said that, this isn't really working. His training was actually first in law and medicine, but his main interest was actually in astronomy and mathematics. And he would actually use it to play a leading role in the emergence of modern science. So what exactly was that role that he was playing? Well, his greatest contribution to science was a critical reappraisal of the existing theories of planetary motion and the development of a new sun-centered or heliocentric model of the solar system. Copernicus concluded, well, the Earth is a planet, and that all the planets actually circle the sun, not just, everything kind of being stuck around the Earth. The only thing that really orbits the Earth is the moon. And although he could not prove that the Earth revolves around the sun, he presented such compelling arguments for this idea that he really kind of turned the tide of cosmological thought and laid the foundation upon which Galileo and Kepler so effectively built in the following century. So when we start talking about the heliocentric model, Copernicus laid this out in his book that he published in 1543, which is, of course, the year of his death. Now, by the time this had come along, the old Ptolemaic system, which, of course, used all the different circles and, various different layers with it, it needed adjustment because it had fallen out of sync because it had to account for all the different movements and stuff that we have going on. Because remember, we have, like wobble of the planet and stuff like that. All that is gently shifting things around. And it's like, well, we want to predict where the planets and stuff are going to be, we're going to need to adjust this model. So Copernicus wanted to develop an improved theory from which to calculate planetary positions, but in the process of doing so, he not only, created a better model, but he freed himself from these traditional prejudices. But, of course, some things still remained. And so let's look at Copernicus' first heliocentric theory when we start looking at this. And so he started off with several assumptions that were common at time, such as the idea that the motions of heavenly bodies must be made of combinations of uniform circular motions. However, one of his big things that he did was, again, not to assume that Earth was the center. And because of that, he had to present a defense that the heliocentric system that was both elegant and persuasive in order to have others take him seriously. Now, his ideas were not widely accepted until more than a century after his death, and were much discussed among scholars, and ultimately had a profound influence on the course of world history. One of the objections, of course, that had been raised to the heliocentric theory was that if the Earth is moving, we would all either sense or feel this motion. So the argument was like, well, if you had something solid, like sitting on the rock, well, it would be ripped from the surface. A ball that was dropped from a great height would not strike the ground directly below it because it would, end up having to move to accommodate for the motion and so on and so forth. But a moving person is not necessarily aware of their motion. And we've all kind of experienced this in our life. So if you've seen like an adjacent train, bus, or ship appear to move, it's actually more likely that we could be the ones moving, all right? Because, think about if you're driving down the highway and there's two cars driving side by side, you're both moving in those vehicles. You just don't necessarily feel like you're moving in those vehicles. So that got, of course, Copernicus thinking about rotation around the celestial sphere. So he argued that the apparent motion of the sun about the Earth during a year could be represented equally as well by the motion of the Earth about the sun. He also reasoned that the apparent rotation of the celestial sphere could be explained by assuming that the Earth rotates while the celestial sphere is stationary, rather than the other way around. Additionally, Copernicus answered that if such a motion would tear Earth apart, because people were, the Earth can't be spinning, well, the still faster motion of the much larger celestial sphere, required by the geocentric hypothesis, could be even more devastating because of the amount of force that would be needed. And so that got him thinking about solar revolution. The most important idea that Copernicus kind of laid down is that Earth is one of the 6 then known planets that revolve around the sun. Using this concept, he was able to work out the correct general picture of the solar system. He placed the planets starting nearest the sun in the correct order: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Furthermore, he deduced that the nearer a planet is to the sun, the greater its orbital speed will be. Now, with this theory, he was able to explain the complex retrograde motions of the planets without using epicycles, and to work out a roughly correct scale for the solar system. The only thing Copernicus really couldn't do, because he didn't have the ability to do so yet, is that he couldn't prove that the Earth revolves around the sun. He could propose it as a theory, but he didn't have all the tools, technical know-how needed to be able to do so. So this, of course, ignited some debate over the different models, because now we have the geocentric model and we have the heliocentric model. Well, in Copernicus' time, few people thought there were ways to prove whether the heliocentric or the geocentric model was correct. And part of this was there's a long-standing philosophical tradition that went back to the Greeks and was defended by the Catholic Church that held that pure human thought combined with divine revelation represented the path to truth. So therefore, they said, well, nature, as revealed by our senses, had to be suspect. For example, Aristotle reasoned about heavier objects, having more of the quality that made them heavy, must fall to Earth faster than lighter objects. It's heavier, so therefore it must fall quicker. However, this is incorrect, as this simple experiment, dropping 2 balls of different weights, will show. However, in Copernicus' day, experiments didn't really carry as much value. They didn't necessarily want to do a lot of testing. So in this environment, there was a little motivation to carry out observations or experiments to distinguish between competing cosmological theories. It shouldn't surprise us, therefore, that the heliocentric model was debated for more than half a century without any kind of testing being applied to determine whether or not this is a valid theory. In fact, the older geocentric model was actually still being taught at Harvard University in the first years after it was founded in 1636, just to give you some context of how long it took for things to change. So this gets us to evaluating the model, right? So we were like, okay, we have this new thing, we're going to start our testing. Well, how can we evaluate the model? So for us today, how could we look at Copernicus' model? Well, anytime there's a new model or theory kind of being posed out, say we got a new hypothesis, we got a new theory, and this is in the field of science, it first needs to be checked for consistency with what's already known. So Copernicus' heliocentric idea passes this test, for it allows planetary positions to be calculated at least as well as the geocentric theory did. The next step is, of course, to determine which of the predictions the new hypothesis makes that different from that of competing ideas. In the case of Copernicus, one of the examples is that if Venus is circling the sun, the planet should go through the full range of phases, just as the moon does, whereas if it circles the Earth, it should not. Also, we should not necessarily be able to see the full phases of Venus from Earth, because the sun would then be between Venus and Earth. But in those days before the telescope, no one imagined testing these predictions. Enter Galileo. Many of the modern scientific concepts of observation, experimentation, and the testing of hypotheses through careful measurements were, of course, done by a man who came nearly a century later. So Galileo Galilei was a contemporary of Shakespeare who was born in Pisa, and much like Copernicus, he began training for a medical career, but having little interest in the subject, he actually switched into mathematics. So what was Galileo's role in comparison? Well, his greatest contributions were in the field of mechanics, particularly in the study of motions and the actions of forces on bodies. He also advocated for the way that we perform experiments or make observations to astonishing ways. So he really has kind of helped starting to drive some of that more modern scientific method. And it was familiar to anyone that if something's at rest, it tends to remain at rest unless it requires some outside influence to start it in motion. Rest was generally regarded as the natural state of matter. Galileo, however, showed that rest is no more natural than motion. When Galileo turned his telescope to the sky, he found things up there that were not the way philosophers had supposed. So what was he exactly studying? Well, particularly he was looking at the way objects accelerate or change their speed or direction of motion. He would watch his objects as they fall freely or roll down a ramp. He found that such objects accelerate uniformly, that is, in equal intervals of time, they gain equal increments in speed. With all this in mind, he formulated these newly found laws in precise mathematical terms that would enable future experimenters to predict how far and how fast objects would move in various lengths of time. So then, sometime in the 1590s, Galileo adopted the Copernican hypothesis of a heliocentric solar system. Now, Roman Catholic Italy, they looked at this, said this is not very popular, for they still upheld the ideas of Aristotle and Ptolemy, as they had powerful political and economic reasons for insisting the Earth was the center of creation. Well, Galileo not only challenged his thinking, but also had the audacity to write in Italian rather than scholarly Latin, and to lecture publicly on those topics. Because for him, then there's no contradiction between the authority of the church in the matters of religion and morality, and the authority of nature in the matters of science. It was primarily, though, because of Galileo and his dangerous opinions that the church issued a prohibition decree stating that the Copernican doctrine was false and absurd and not to be upheld or defended. And so, one of the things that Galileo did is he also had some astronomical observations. And while it's not certain who first kind of conceived the idea of combining two or more pieces of glass to produce an instrument that enlarged images of distant objects, Galileo first heard this discovery, and without having seen an assembled telescope, decided, you know what, I'm going to make one of my own. And he made one with a 3 times power magnification, which made, of course, distant objects appear 3 times nearer and larger. And this leads us to the start of the birth of the modern telescope. On August 25th, 1609, Galileo demonstrated a telescope with a magnification of 9 power to government officials in the city of Venice. Now, with a magnification of 9 power, the object appeared, of course, 9 times closer. And this obviously had some military advantages. If you can see your opponent before they can see you, that's going to be pretty valuable. And actually, Galileo was rewarded for it. Now, others, of course, had used the telescope before Galileo to observe things on Earth. But what made Galileo special is that he decided, you know what? Rather than simply just looking around me, what if I took that same thing and turned it to the heavens? So, before using his telescope for astronomical observations, he had to first devise a stable mount, and he also needed to improve the optics. Once he had done this, he was able to increase the magnification to 30 power. So now, he's got so much power. What he's going to do? Well, he's going to be able to go beyond what the human eye can normally see. At the time, human eyes were believed to be the final arbiter of truth about size, shape, and color. Lenses, mirrors, and prisms were known to distort distant images by either enlarging, reducing, or inverting them, and spreading the light into a spectrum. Galileo undertook repeated experiments to convince himself that what he saw through that telescope was identical to what he saw up close, because he wanted to prove that he wasn't just seeing things. Only then could he begin to believe that the miraculous phenomenon the telescope revealed in the heavens was actually real. He began his late astronomical work in about 1609, and when he did, he found that many of the stars that were too faint to be seen with the unaided eye were suddenly visible with the telescope. In particular, he found that some nebulous blurs in the sky resolved into stars, and that the Milky Way, which was at that point just a strip of whiteness across the night sky, was also made of a multitude of individual stars. And so that's going to get him into centers of motion, because examining planets, Galileo found 4 moons revolving around Jupiter in times ranging from just 2 days to about 17 days. This discovery about the moons was particularly important because it showed that not everything has to revolve around Earth. Furthermore, it demonstrated that there could be centers of motion that are themselves in motion. Defenders of the geocentric view had argued that pretty much if the Earth was in motion, then the moon would be left behind because it could hardly keep up with a rapidly moving planet. Yet, when he looked at Jupiter, and he looked and saw the moons, and he saw them orbiting Jupiter, they were doing exactly that. With this telescope, Galileo is able to carry out the test of the Copernican theory that we have talked about, of course, and he did this based upon the phases of Venus. So within a few months, he found that Venus goes through phases, much like the moon, showing that it must revolve around the sun, so we can see the different parts of its daylight side at different times. Now, these observations, of course, could not be reconciled with Ptolemy's model, in which Venus circled about the Earth, because in that model, Venus, while also showed phases, ended up showing the wrong phases in the wrong order from what Galileo was able to observe through the telescope. So Galileo's work, again, was very important because he observed that, for example, the moon, it had craters, mountain ranges, valleys, flat and dark areas that he thought, maybe this is water. These discoveries were very important so that, hey, maybe the moon is not so dissimilar to Earth, suggesting that Earth could also belong to the realm of celestial bodies. Now, after Galileo's work, it became increasingly difficult to deny the Copernican view, and the Earth was slowly being dethroned from its central position in the universe and given its rightful place back as one of the planets attending the sun. And so we're going back to this cosmic conception here. So the new ideas that Copernicus and Galileo proposed out really began a revolution in our conception of what the cosmos is and what we expect from it. It became evident that the universe is a vast place and the Earth's role in it is relatively unimportant. The idea that the Earth moves around the sun like the other planets raised the possibility that there might be worlds themselves, perhaps even other worlds that support life. Now, today, most of us take these things for granted, but 4 centuries ago, these concepts were relatively frightening and even heretical for some, or intensely stimulating for others because it gave them a chance to ask questions of what else is out there.